Historically, germanium, silicon germanium were first grown by molecular beam epitaxy. This is a system in which essentially the elemental semiconductors, pure silicon, pure germanium, are placed inside a vacuum chamber. They're heated. Usually silicon and germanium are heated up by electron beams, although some other elements can be heated thermally, until atoms are basically subliming off the solid material into the vacuum chamber. What then happens is that the wafer, which is suspended in this growth chamber, is subjected to this flux of atoms or molecules, and these stick to the substrate. The substrate is, of course, heated up so that the quality of the crystal is acceptable. And a lot of early work was done with this. There's an example on this slide of what was the previous record for mobility in germanium channels from the mid-90s. And the drawback here is that to grow these thick graded buffers, a lot of these solid sources are completely consumed, and then the only way to refill them is to completely break the vacuum. And the vacuum needs to be very good for molecular beam epitaxy because we need the atoms from the sources to arrive directly on the substrate without being deflected by atoms of gas in the chamber, and we also don't need any impurities in the chamber to arrive on the substrate faster than these atoms of the material we're trying to grow. So a very good vacuum is critical in MBE, which is no good if you have to keep breaking a vacuum to put new material inside. So as a research-based tool, it's relatively interesting, but as an industrial tool, it's not really acceptable to be doing this. And so some work continued with attempting to grow buffers with a thinner structure, but as you will see in Ignite, a lot of the material is actually grown by chemical vapor deposition. And industry has moved to chemical vapor deposition. This is a much more scalable technology. This works at various pressures. The system used most often for industry now is reduced pressure, and this is a few hundred torr, something like that, in terms of pressure. In this case, gaseous precursors arrive in the growth chamber. Here the vacuum is not so critical because there is a background of gas, usually hydrogen, to bring these precursors through the system. These precursors, silane and germane, or various chlorosilanes in some cases, or even disilane. So these chlorosilanes, chlorosilicates, and germane, these are analogues of methane, but using silicon and germanium. They pass through the system, and the hot wafer is the reaction substrate for chemical reactions. So this means two things. Firstly, that the growth rate is strongly dependent on the substrate temperature. In fact, as you can see, it's exponentially activated by the substrate temperature, mainly because you need free sites on the substrate, so you need hydrogen to dissolve from the substrate to allow a chemical bond to be exposed for one of the precursor molecules to attach. The second thing that it means is that the precursor molecules only attach in chemically favorable sites. And this means that the crystal is almost perfect. There is no incentive for these precursors to attach in the wrong places. They always attach in the right places because they have to attach to the chemical bond. So very high quality material results. The drawback is that there is a strong dependence between the substrate temperature and the growth rate. And in the case that, as we saw, you need a low temperature to grow these silicon germanium structures with pure germanium channels in order to avoid relaxation and interdiffusion, to grow at such low temperatures means the growth is going to be very slow. And then in order to optimize the graded buffer, or the reverse graded buffer, there's a strong trade-off between the temperature of the growth, which a higher temperature means these thicker layers grow more quickly, but a lower temperature may be needed in order to optimize the defect structure or the roughness of the material. However, being an industrial tool means that there is a large amount of expertise behind this system, so a lot of knowledge is building up on how to grow the best quality material, and in some cases even virtual substrates are available at a commercial level. The system, however, that we use at the Politecnico di Milan uses a plasma to enhance the chemical vapor deposition. And critically, the plasma has a low energy. That means that instead of being, for example, a typical radio frequency plasma where the ions have a large energy and they can damage the crystal, and in fact this kind of plasma-enhanced CVD is useful for amorphous materials such as oxides and nitrides. In this case, the low energy plasma-enhanced chemical vapor deposition means that the ions do not have such a large amount of energy, means that the crystal is not damaged. The reactive conditions in the plasma, the high density of electrons, however, means that these gaseous precursors are cracked into very reactive radicals. And these neutral radicals are responsible for very high growth rates. And the growth rates are now not dependent on the substrate temperature because the chemistry is happening in the plasma. The energy is provided by the plasma, not the substrate temperature. This means that we can grow at 5 to 10 nanometers per second without any influence of the substrate temperature. Of course, this means that the growth is not necessarily of high quality. In fact, it's now up to the operator to balance the growth rate and the temperature, because if we grow too fast at too high a rate, the material may not even be crystalline. However, this extra flexibility, with great power comes great responsibility, but this extra flexibility means that we can grow very thick layers, we can optimize the temperature to get the best quality possible, and then by reducing the plasma density and reducing the gas flows, we can also grow these quantum wells at high precision, quickly enough to avoid relaxation and quickly enough to avoid contamination by background impurities, but also slowly enough to have good control of the composition.